So here's the given equation and a couple of additional conditions that r equals p over q pi. P and q are positive integers, and r is an angle contained in this interval. The goal is to find p plus q. So let me write down this equation yet again. Now what I'd like to do is to this term here, I'd like to apply what we call the change of base. And I'll actually do it to both terms. So let's see. So that's log of cosine r over log sine r. That should have been tangent. So it's log tangent r over log cosine r equals 1. Now recall one thing. Remember that tangent is the same as sine over cosine. And now what I'd like to do is to this term here, this numerator, which looks like this, I'd like to apply this expansion property only to this numerator. So I've expanded this numerator into these two terms based on this identity, and I dropped the parentheses, you don't really need them. Now what I'd like to do is I'd like to apply the property that says a plus b over c implies that this is a over c plus b over c. You see what I'm saying? Just taking one term and breaking it apart into two terms with the same denominator. Let me apply that to this thing right here. And you can see here that this is actually just 1. And what I can do is we can add 1 to this side. And now I would actually like to use a couple of substitutions. Why don't we let x equal log cosine r and let y equal log sine r, so we can rewrite this equation with x's and y's instead. So now my temporary goal is to find the value of x and y. Once I know x and y, I can go here to discover r. And once I know r, I can go back here to see something about p and q, because that is the overall agenda. So back to this equation here. I have two fractions that are being added. If you want to add fractions, you have to have a common denominator. And so I'll multiply this one top and bottom by x, top and bottom by y, and this gives us x squared plus y squared over xy equals 2. And then I can multiply both sides by xy, because I don't knock out this denominator. So it's x squared plus y squared equals 2xy. And if you bring this term over to the other side and sandwich it in between the two terms that were already there, you get this here. And as it turns out, this here can be factored into the following. It becomes x minus y times x minus y. That is the factorization of this into this, because if you distribute, you'd get this back. So because these are identical, it's really just x minus y squared equals 0, right? Because it's two of the same object. And if you square root, it's just x minus y equals 0, because plus or minus the square root of 0 is just 0. And this tells you and I that if you add the y, it tells us that x equals y. Now, what exactly were x and y? X and y were these items here. So if x and y are equal, then this equals this. So here's what we have. We have log cosine r equals log sine r. These two logs have the same invisible base of 10, so these knock out. So we have cosine r equals sine r. Where on the unit circle does this work? Use the unit circle to interpret what's going on. Remember that on the unit circle, cosine is like the x coordinate. Sine is like the y coordinate. So this is kind of like your x coordinate, and this is like your y coordinate. Where on the unit circle does the x coordinate equal the y coordinate? Well, that works here, and it also works there. And I propose that on the unit circle, these are the only locations where the x and y coordinates are equal. But, however, for this problem, this location here is no good, because the x and y coordinates here are both negative. So you would be depositing a negative value here and there. And for logarithms, you cannot have a negative base or a negative argument. So for that reason, this location is discarded and the only valid location is this here. So what I'm saying is that from this equation, we have discovered that r is pi over 4. R is an angle, and that angle has to be pi over 4 radians here, because there, the coordinates of this point are square root 2 over 2, comma, square root 2 over 2, which means that cosine of r equals sine of r, which is the condition that was just discovered. So what do we take away from this? We take away this fact, r equals pi over 4. That, however, is not the final answer, because the final answer was to find p plus q. But we can now proceed to finish this problem, because we know that r equals p over q times pi. But we just discovered that r is pi over 4, which can go right there. So we have pi over 4 equals pi over q times pi. You can multiply both sides of this equation by 1 over pi, which knocks this out and this out. So we have 1 over 4 equals p over q. Now, here's the issue that I have with this problem. This is the only equation that we have to work with. You could never really know what p and q are exactly, because watch. This could be like 4 over 16. P could be 4 and q could be 16, because when you reduce 4 and 16, you get 1 over 4. Or instead of 4 and 16, we could have like 100 and 400, because p could be 100, q could be 400. After all, when you reduce this, it's 1 over 4. So we know the relationship between p and q, that q is 4 times bigger than p, but we'll never actually know what p and q are individually. That's what I'm proposing to you. However, maybe in the directions they forgot to say something. Let's take a leap of faith. Let's just pretend that we can make a direct comparison here. Let's pretend they wanted us to assume that once you have this here, this fraction is fully reduced, that p could be the top and that q could be the bottom. And in that instance, p plus q would be 1 plus 4, which of course equals 5. So I am not all that satisfied with this conclusion because of this dilemma here. We can never know p and q, we can only know the relationship between them. Maybe there's something in the directions that I missed, but if you happen to find that specific technicality, let me know. But as is, I'll submit to you that this is the final result.